So let's start with the differentiation and its application. Here are some of the standard derivative function which we are recalling, like derivative of x to the power n. What is n? X to the power n minus 1. Similarly, for exponential it would be the same, and for constant it would be 0, and a to the power x, a to the power x, and then log a, and derivative of log x would be 1 by x. Similarly, there are some other additional functions which we will see like later in the preceding lectures, like derivative of e to the power ax, that would be a e to the power ax, and then derivative of log of ax, this would be 1 by ax into a, that would be same derivative 1 by x itself. And here are the basic rules of differentiation. Like if we are taking the derivative of a k, and this is a function f of x, then k being a constant, it would be pulled out and it would be derivative of f of x. And similarly, for derivative of f of x function plus or minus g of x function, that would be derivative of f of x plus or minus derivative of g of x. And if there is a product rule, this is the product rule. Like first, one time we are keeping one function as it is, we are taking derivative of this, then second function as it is, and derivative of other function. It is popularly known as UV rule. Like suppose derivative of x we are taking with respect to uv, here u and v are function of x, then what we are doing, we are taking v derivative of u with respect to x, and plus u derivative of v with respect to x. Similarly, here it is f of x by g of x, which can be u by v rule. This is like second function square, and then second function as it is derivative of first function, then first function as it is derivative of second function. So popularly uv rule, derivative of x with respect to u by v, that would be, first we will do denominator square, then v derivative of u with respect to x, and then minus u derivative of v with respect to x. This is our uv rule function. This uv rule is very important as it has many of the questions from it. Now we will see something which is implicit function. So first let's understand what is implicit function. Like this is the example from the textbook. Suppose we have got one equation which is 3x square plus xy plus y equal to 0. So this function can be explicitly written either in terms of x or in terms of a y. Considering the simplicity, we will write this in terms of y in terms of x. So it would be 3x square. From the second term, we are pulling the y common. Then x plus 1 equal to 0, which implies we can write y equal to 3x square upon 1 plus x. So here we have wrote entire y in terms of x. Like if we have got like any of the equation, so what we can do, we can make the equation in the simpler terms, like either in terms of x or in terms of y, and then we can choose to take the derivative of it. Now suppose we want to take the derivative of this function. So how we will do? Like this is our u and this is our v. So here we can apply uv rule. So derivative of y with respect to derivative of x, what it would be, like first denominator square, and then our denominator as it is Then here what we will do, derivative of minus 3x square, and then here minus sign, and then our u as it is, which is minus 3x square, and derivative of denominator 1 plus x. So what it will be, like derivative of 3x square, which is minus 6x, minus 6x into 1 plus x, and here minus and minus will be plus, plus 3x square, and here it would be 1, so upon 1 plus x the whole square. Now let's solve for numerator. So numerator it would be minus 6x minus 6x square plus 3x square upon 1 plus x the whole square. So here 3 minus this, how much it is? It is minus 6x minus 3x square upon 1 plus x the whole square. So from both this we can take minus 3x common. So inside it would be 2, and here it would be minus x. No, it would be plus x, and then 1 plus x the whole square. So like this we can solve the implicit function. So now let's take some of the other derivative of a function from the example 1. Say we are having the derivative, for example, like log of xy square, and here it is given like it is y, our function y in the terms of x, and we need to take the derivative of it is. So what we can do, here log of, as we know, log of a plus log of b equal to log of a into b. This we all know. So here we will be applying the property of the logarithm, like our log x plus log y square, and since log of a to the power b equal to b log a, this is the property of log. So log x plus 2 log y, and this is our y function as in the question. Now we have got y function. Now let's differentiate. So what we will get after differentiation, dy by dx, derivative of log x with respect to x is 1 upon x, plus 2 will be constant, derivative of log y will be 1 upon y, and this would be dy by dx. And here this wasn't log y, this was f, function f. So this is derivative of function with respect to x. And now let's solve another question like dy by dx. We need to find for what? For equation x cube plus y cube equal to xy. So let's differentiate with respect to x. Here as x and y both are our dependent variable, independent variable. So we can't like directly consider them as a constant. So derivative of this with respect to x, d by dx of x cube plus d by dx of y cube plus d by dx of xy. So what it would be? Derivative of x cube would be 3x square. Derivative of y cube will be 3y square dy by dx, and here it would be chain rule. So first like we are treating this as u, this as v. So first x as it is, derivative of x with respect to y plus our y function as it is and derivative of y with respect to x. Now as we can see like here we are having dy by dx term, here also dy by dx term. We will be keeping all the dy by dx term on the left hand side together. Here one mistake we have done like x derivative of y, then y is constant and here it should be derivative of x, which would be 1. So dy by dx 3y square minus x equal to here it's y minus 3x square. So dy by dx that would be y minus 3x square upon 3y square minus x. Now we will be considering the logarithmic differentiation. Like for some of the functions where we have to apply the property of the logarithms, like here as we know, if we are having the function with the power x to the power n, then we can take it as n x to the power n minus 1, where n is our any real number. Also for a raised to x, we can write a raised to x log a, where a is some of the positive real number, like a is our constant. For both of these formula, but it cannot be used in the differentiation kind of a function. Like if f of x is raised to the power g of x, like x to the power x and x to the power same function of x. So here we can't directly apply this formula, which is derivative of this with respect to this, like x to the power x minus 1. Similarly, x to the power x log x, which was here. So these are not valid here. Like in such of the cases, we use derivative first and then we solve these particular questions. So let's begin with this first is question. Like y is given as x to the power x. So in such cases, since this is x and it is also to the power x, like f of x to the power g of x. So first what we will do, taking log on both sides. So this would be log y, and this power will come as the coefficient log x. Now we will apply differentiation. Differentiation with respect to x. Let's give this as equation number 1. So derivative of log y, which would be 1 upon y dy by dx, and here uv rule, u, like this is our u, this is our u, this is our v. So let's apply uv rule. So x as it is, derivative of log x plus log of x as it is, derivative of x. So what it would be, 1 upon y dy by dx equal to x into derivative of log x is 1 upon x plus log x as it is, and derivative of x is 1. So this will be cancelled out. Here it would be left 1 plus log of x. And here we were having this original y dy by dx. So this y we will be shifting here. So dy by dx is equal to y into 1 to the power log of x. But from 1, what we know, y equal to x to the power x. So dy by dx is equal to x to the power x 1 plus log of x. So this is the result. And after this, like there are some second and higher order functions, like where instead of taking derivative for the first time, we are again differentiating it, and we are taking the second order, and further nth order, like this we are taking higher order derivative. Like this is the first order derivative, then outside again differentiation, so it's became second order derivative, and it is written as d square y dx square, and here our function f of x. So this is the general equation for finding nth order derivative. So now suppose for few of the questions we will be solving. Find second order derivative, which is d square y by dx square. Let's solve for the question from the textbook, which is y is equal to log of x. So how we will solve this? First we will differentiate with respect to x. So this would be derivative of x of log of x. So it would be derivative of log x is 1 by x. So this we got the first derivative. Now again for this first derivative dy dx of y, this we will be solving. So this would be d square y by dx square, which is equal to dy dx of 1 by x. As we know derivative of 1 upon x, we can solve it like dy dx of x to the power minus 1, derivative of 1 upon x minus 1 upon x square. So this is the second order derivative of log of x. And now in the example 9 of the textbook, what it says, like x is a function of t square upon 1 plus. In this question, the concept of parametric function and also the higher order both are involved. So that's why we can go with this question. T square upon 1 plus t and y is equal to t upon 1 plus t. And here we are supposed to find second order derivative. So whenever the function like x is in terms of t and y is also in terms of t, so what we do, we differentiate x with respect to t and then we differentiate y with respect to t, and then using this we are finding dy by dx is equal to dy by dt by dx by dt. This concept is known as parametric form of differentiation. What it is known? Parametric form of differentiation. And similarly, for having the second order derivative also we will be taking like the second time we will differentiate, like this whatever we are getting through this again we will differentiate. So here the second order derivative would be d square y by dt square is equal to d square y by dt square by d square x by dt square. This was the concept, and now we will solve this problem. Like x is equal to t square upon 1 plus t. So our dx by dt, that would be denominator square, and then denominator as it is, derivative of numerator 2t minus numerator as it is, derivative of denominator which is 1. Then what it is coming? Here it is 2t and here it is 2t square minus t square, which is t square plus 2t upon 1 plus t the whole square. And then this was our dx by dt. Now we are having y, and y is what? T upon 1 plus t. So denominator the whole square, denominator as it is, derivative of numerator minus numerator as it is, derivative of denominator. So it would be 1 upon 1 plus t the whole square. So now we will compute. This is our dy by dt. this term. So now we will compute first order derivative, which is d dy by dt by dx by dt. So this would be dy by dt, which is 1 upon 1 plus t the whole square, and dx by dt is t square plus 2t upon 1 plus t square. So this would be cancelled, this would be cancelled, and we will be left in with 1 upon 2t plus t square. This is our first order derivative. And also one thing, this chain rule, this can be solved with the chain rule. So don't consider this, like this would be like too confusing. We will see how to solve it with chain rule. So second order derivative, which is dy dt, as second order first order derivative which we have obtained was in the form of t. So that's why dy dt of what, our y1, and then dt by dx, like for compensating this particular term which we are getting, dt by dx. So y1 we have got already, like here. So what we have to do, d by dt of 1 upon 2t plus t square into dt by dx. And do we have dt by dx? We have already calculated dx by dt. So dt by dx would be equal to 1 upon dx by dt. So derivative of this, what it would be, u upon v rule, or directly we can solve with the formula derivative of 1 upon x minus 1 upon x square. So derivative of 1 upon x minus 1 upon 2t plus t square the whole square into derivative of denominator, which is 2t would be 2 plus 2 plus t square derivative will be 2t, and into dt by dx, that would be reciprocal of our dx by dt. So dx by dt we have got this particular term, so that would be 1 plus t square in the numerator, 1 plus t the whole square in the numerator, and the other part which is 2t plus t square over here. So let's check whether do we have any cancellation. So see, here we can take t common, so it would be minus 1 upon 2t plus t square the whole square, 2 plus 2t, and then 1 plus t square, and from denominator we are taking t common, t into 2 plus t into 2 plus t. So here are we getting anything common? Here we are having 2 plus 2t, 2 plus 2t, and from here also we can take a t square common, this from this term, minus 1 upon, suppose here we are pulling t square common, so it would be 2 plus, like t we are taking common from this t square term, so it would be t square 2 and t, and here it would be square, and numerator 2 plus 2t into 1 plus t the whole square upon t upon 2 plus t. So this t into this t will be tq, and here it is t plus 2, t plus 2 cube, and then the numerator this minus sign, and let's take this 2 common, 2 into 1 plus t into 1 plus t the whole square, so it would be minus 2 by t cube into 1 t plus t whole cube upon 1 plus t the whole cube. So this is our second order derivative. So important part here it is like how we are considering this in the terms of parametric form. Like first we are reaching dx by dt and then dy by dt, and then we are calculating dy by dx in the terms of dy by dt and dx by dt, and here we are applying chain rule, like here we are applying, I will take some different color, like here we are having our chain rule, like the derivative of x then the compensation of the t component. So this was all for this part.